Nous avons le plaisir en fait d'accueillir Minik, qui est professeur à l'Université de Copenhague et qui est aussi chercheur au Muséum d'histoire naturelle du Danemark. Il a fait son doctorat à l'Université de Copenhague en 1989 et c'est un spécialiste en fait de la formation des continents terrestres, de leur stabilisation, ainsi que de l'émergence de la vie et de son influence sur les cycles biogéochimiques. Voilà. Merci, Minik.
Thank you very much. I don't know if I'm in charge of getting this to work. That probably wouldn't work. Anyway, I can start with a slight introduction to what I'm going to say. First of all, thank you for inviting me. I will be unable to speak in French, so you have to apologize for my English. Besides being a geologist working in the Arctic, I also praise myself of being an amateur Inuit. I was born in Greenland, but only at the amateur level. What I'm going to talk to you about today is the study of the Arctic through the eyes of a geologist and Ta-da! Yes. So what I'm going to talk to you about today is how we can study many important issues of how our planet works through working in the Arctic, but actually not performing Arctic science per se. I think that's a very important aspect when talking about the Arctic Research Initiative here, is that a lot of the research that takes place in the Arctic actually doesn't deal with Arctic phenomena, but it's a fantastic research lab for many other fields of science. And obviously, the study of the origin of the continents on Earth and the origin of life on Earth are global problems and of interest to everybody, even outside the Arctic community. And the part of the Arctic that I focus on is the part we see here, a particularly nice part, that is Greenland. We see the southern tip, and we see the northern part of Greenland disappearing into the Arctic winter. This is a piece of land that has a tremendous, it's a tremendous research lab for studying all kinds of processes related to how our planet functions and how it was all formed. I'd like to start, since we are a mixed congregation here of people, even including social sciences and humanities, to introduce a very important principle. In geology, it was formulated by Steno, who was a Danish scientist. In 1668, he got a fantastic revelation and piece of insight. That is that if you pile stuff on top of each other, what's in the bottom came first. And this is a typical scientist's desk, and what it consists of is strata that contains information that can be retrieved. If you dig down through the strata, you can retrieve older and older information and learn about the times in which it was formed. And this is basically what geology is about. It is about studying the pile of strata that has accumulated on Earth since a long, long time ago. So how long is a long, long time? Well, I think it's appropriate to use a graph here produced by NASA. It's a diagram that shows all time that existed in the universe. Time was invented here 13.7 billion years ago. It's been progressing up till now. And what's interesting, I think, what's exciting to put to scale what the geologic record is, basically that the geologic record starts here. That means that we have strata stacked on top of one another that contains information about all time from here to here. That is almost 1/3 of all time that existed in the universe that's recorded in the rock strata. And the oldest rock strata we have on the planet are here in West Greenland, a place called Isua. And that means that from Greenland, we can actually read and understand 1/3 of the history of the universe. So that's our little task that we will try to pursue here. So why is Greenland such an interesting place for geologists? Well, if you fly by, we are now flying into Isua, take you along on a trip to these old rocks, back to this, basically the dawn of time. You can see here the Greenland ice cap has not just recently, but through many thousand years, retreated from the land and left naked rocks that have since not been disturbed by nasty things like soil and plants. So you just have rocks sticking out of the ground, basically. And This has been identified since more than 200 years, and geologic research has been taking place in Greenland since more than 200 years, because we have such a, geology is basically like an open book when you work in a place like Greenland. So what do we see if we fly into this area that is so amazingly old? Well, here is an example of what we see, and I can imagine you are all very excited by what you see here. It's a beautiful and very interesting piece of rock. But what's special about this rock, I think there are several things we can read from this rock. One is that we have these sausage-shaped objects that are kind of, you can see in the rock. These sausage-shaped objects we know from modern geology, and we know that these form when a volcano erupts underwater. So what you see here is the first evidence of the presence of an ocean on our planet. Before we found these old rocks, we actually didn't know that we had oceans 3.8 billion years ago when these rocks formed. So that's one astounding piece of information we have. Another, I think, equally astounding piece of information we get is that this thing has been sitting, it took about maybe 30 seconds to form this, took another 30 seconds to form this, and it's been looking like this ever since. And that shows to us that the planet we live on is a particularly boring place. Absolutely nothing, almost absolutely nothing, takes place even over 4 billion years in parts of Earth. So we always talk about Earth as a very dynamic planet, but I hope to demonstrate to you, although we see, and we have heard many talks about the little wiggles we have in the present and near present time, but if you look on Earth over a billion-year time scale, it's an amazingly stable construction, climate-wise, environment-wise, and everything else-wise. And as you can see, you can preserve features for 4 billion years without disturbing them in the crust of the Earth. So that is very interesting. These little rines we see, the black rines, are formed by reaction of the magma with the ocean water. And they, as they do so, they suck up a little bit of the hydrogen and oxygen from the ocean water. And from the information stored in the isotopes in this, we can actually reconstruct the magnitude of the ocean 3.8 billion years ago. And we can determine that Earth have lost about 25% of its inventory of water since the past 4 billion years. That's a lot of water, you could say, but on the other hand, you can say it's good news because since 4 billion years, we have only lost 1/4, so in a foreseeable future, we'll still remain a watery planet, we can safely say. Among the rocks in this very ancient complex of rocks, we also have sediments that formed by the settling of mud and sand through the water column in the ocean, and they form these very nice features that, again, is something we can recognize from the modern Earth. Nothing exotic about it. These are mud flows, mud avalanches that have cascaded down some submarine slope about, again, 3.8 billion years ago. In quiet times between the avalanches, we would have a very slow settling of clay in the ocean as we do today. So these layers may be accumulated with a rate of 1 millimeter per 1,000 years, something like that. So these particular ones are interesting because they record the everyday life, I was just about to say, everyday conditions in the ocean 3.8 billion years ago. So for that reason, it would be interesting to take a little bit closer look at them and see what they can tell us about the ocean back at these early times. And what we see in the microscope, here's about 0.5 centimeter of a microscope slide. What we can see when we look down the microscope is that we can see layers, very, very fine, less than millimeter thin layers preserved in this rock also. Again, a testament that Earth is actually not that dynamic. These things, you can see there are different colors. There are some black or dark gray, and there are some colorless layers. If we look closer at them, it turns out the colorless layers are probably volcanic ash that settled rapidly through the water column and formed these layers, whereas this is basically what was once clay that settled very slowly and deposited at a very slow rate. And if you look at the minerals, it consists of a mineral we call white mica and another one called quartz, which are both distinguished by being colorless. So of course, now the plot is thickening. Why are these layers then black since they consist of only white minerals? Well, if we look closer, it turns out that the white or colorless minerals contain little inclusions of a mineral, which we can identify as graphite, which is elemental carbon. And you can see that there's an enormous wealth of these little carbon grains throughout these dark layers. It turns out that these carbon grains are confined only to the clay layers, to the slow settling things. And the best way to interpret this is, of course, that carbon settled very slowly out of the ocean and deposited on the bottom. So that is exciting for many reasons. Of course, we all know that carbon is an essential part of living organisms, but also we know that the Earth's surface environment is oxidized, not only through the activities of life, but intrinsically oxidized, such that carbon is always tied up with oxygen, either in carbon dioxide in the atmosphere, bicarbonate in the water, or carbonates in the crust. And if we have the carbon separated from the oxygen, it's usually a sign that some living organisms have been involved in the process. So what that probably means is that in the early ocean, living organisms were able to reduce carbon, and the dead organisms would settle to the ocean floor. Okay, that's good, but maybe we need more than maybe. So what we can do is look at the isotopic composition of the carbon, because it turns out that when living organisms sequester carbon out of the ocean, they fractionate the isotopes, and they produce carbon that has a deficit in the 13C stable isotope of carbon. And that value for biomass in the ocean today is about -26. If we look at the rocks from Greenland that are that old, it turns out that they also share the same composition of the isotopes, which again is probably as close to a bulletproof proof you can come up with, that this carbon was actually derived from living organisms. Some people have been speculating that maybe the carbon in these rocks is very, very rare little trace components that would be easily to overshadow with modern biomass of some fashion. And if some of you have the feeling that this is not the nicest PowerPoint graph you ever saw, there's a reason for it, and that is that I wrote this diagram with one of the rocks from there, just to prove that carbon is not a trace component. You can actually write with it. So carbon is very plentiful in these rocks, and that translates into the observation that the life that is responsible for generating this reduced carbon could not be amateurs in the field. It could not be the first life on Earth, because to be able to have a high bioproductivity in the open ocean, you need to be a sophisticated organism. So it seems that we are looking at a relatively high level of microbial life already at 3.7 to 3.8 billion years ago. So another sign we see from the activity of this life is banded ion formation. This is the issue of banded ion formation. For those in the social sciences, you might have heard that there is a big plan for an international exploitation of this particular ion formation in Greenland, involving a lot of migrant workers and everything else. But let's leave that aside now and just look at the rock, because what this is again a testimony that we had some redox activities taking place in the ocean that was able to oxidize reduced iron and deposit it as ion formation. If you look into the rocks, it also turns out that uranium and various other redox active components were being processed by some kind of process, which is best described, I think, as some kind of photosynthetic, maybe not producing oxygen, but some kind of photosynthesis was active in the ocean 3.7 billion years ago. So that is another very important piece of information, that basically there's no major innovations on the planet in terms of the biosphere since 3.8 billion years ago. This rock is also interesting from another point of view. We have been talking about the change between ice ages and interglacials here, from 1% changes in insulation due to Milankovitch forcing and these various other things. But at the time when we had this liquid ocean on the surface of the planet, the insulation was 25% less than it is today. It's known as a faint young sun paradox. And the paradox is that although we received 25% less energy from the sun, we still had a liquid ocean on the surface of the planet. And this has classically been proposed solved by basically cranking up the CO2 content of the atmosphere to about 0.3 bars, or maybe all the way up to 1 bar of CO2 in the atmosphere on the early Earth. But it turns out that the minerals we find in these ion formations are incompatible with CO2 contents in the ocean and atmosphere much higher than it is today. Maybe it could be 10 times higher or something like that, but nothing up in several orders of magnitude higher. So again, these ancient rocks not only testify to the presence of life in the environment, but they also tell us about the composition of the atmosphere and a lot of other features that we might be interested in. So here we have a rock that in one shot tells us that the climate on Earth has been rather uneventful for 4 billion years, and that actually the CO2 content of the atmosphere has not varied very dramatically, which is a different issue dramatically when you're talking billion-year timescales than when you're talking 1,000-year timescales. So I'll now make a jump forward in time. It doesn't look like I'm making all the way to the present, but this is actually from an expedition 2 years ago where we had this nice vehicle for an expedition ship to East Greenland. Because we now have established from Greenland that life emerged and was active before 3.7 billion years ago. And then followed a number of very, very boring years. Some people have called the period between 2 and 1 billion years as the boring billion, because nothing happened, it seems. So Earth was a boring place. But at about 750 million years ago, things started to change, and we have that recorded in Greenland as well. In the 1930s, an expedition went up to North Greenland to establish a field station to study the geology of Northeast Greenland. That's the field station we see there. And they were very successful in mapping out some very interesting geology that covers the period called the Proterozoic, that is before animal life was on the planet, and into the period where animal life evolved. And they actually found the first amphibians that went on land. The first time that a fish basically crawled on land happened here in Northeast Greenland and was found from this expedition. Here's the house. And a little interesting aside to that is actually that this house was built also in response to a battle between Denmark and Norway over the authority over East Greenland, and it was solved in the International Court in Hague. And I think that was the last time that was a quarrel over land in the Arctic, and you probably have seen headlines about the rush for the Arctic and the battle of the Arctic and all kinds of things. But it turns out that that is non-existent, and it seems like all the nations around the Arctic are completely in agreement that the borders are what they are, and they should all be settled by international law, as it was done for this particular piece in the 1930s. And that was the basis for Greenland being one nation today and the only autonomous Inuit nation in the world today. So geology there is wonderful. And here is in these old houses, we have books where people put their little entries when they've been here. This is a guy called Paul Hoffman from Harvard University. He says, doing geology on Ella Island is like going to heaven without having to die first. So this is a very clear and precise description of what geology in Greenland is like. And you can see from this photo taken out from the window of the house why geology in Greenland is so wonderful. See, you have all these strata, like the desk you saw early on. They've stacked up for about 500 million years. 500 million years of strata are stacked up. And then they're very, very gently folded in such a way that you don't have to climb a very, very steep cliff to see everything, but you can walk on your city shoes along the coast, and you can walk through 500 million years of Earth evolution on a nice sunny afternoon. So that is the reason for his statement that the geology is really, really spectacular. And you can see every rock. You're not missing one strata in a sequence like that. And what do you see if you go on that little stroll along the coast? Well, in the Proterozoic, that is before the emergence of the animal life, everywhere you see these hummocky features, which are called stromatolites. They are formed by microbes on the ocean floor. You can imagine that before animals, the ocean floor, the whole surface of Earth was probably like the innermost corner of a refrigerator after you return from vacation or something. There's some kind of slimy substance all over everything. And that was like the situation for the surface of the planet in the large part of Earth history, because we had only microbial life for more than 3 billion years. There was no reason for constructing anything more complex than microbes. So this is what it looks like. But if you go further up the section along the coast, you come into something strange. This looks nothing like we saw before. This is a rumble of rocks and clay and everything else. This is tillite. This is basically a glacial deposit that suddenly was dumped on top of these algal mats. By paleogeographic reconstruction, we can see that these tillites were deposited on the equator at sea level. So they are right on top of marine deposits, and they are formed at equator 750 million years ago. So here is a big puzzle, and it turns out that you find these deposits in many other places on the planet, and it turns out that Earth was affected by an event called the snowball Earth event. There were maybe several snowball Earth events between 750 and 600 million years ago, where the entire planet down to equator was covered by ice. The whole thing sealed off, and it must have been a tremendous talk about climate crisis. This is something that would be rather devastating. It surely must have been somehow an evolutionary challenge to the life that existed in the ocean. So when we go further up this section, we get out of those glacial deposits. Something strange happens. Actually, you observe that these algal mats don't exist anymore. There's no more algal deposition on the ocean floor. And instead, you get tracks from somebody who moved through the mud. And those somebody are the first animals that started roaming the surface of the planet. So this big global glaciation caused some kind of disturbance of the Earth system that put so much challenge on life, some speculate anyway, that basically the solution came out in the form of the metazoans, and that they started to roam around. And you can see these tracks in the petrified mud from East Greenland. You go a few meters further up, and you start to see the first skeletal parts deposited here. These are shells from some kind of organism that as soon as all the first things had ate all the algal mats, and there were no more of those, they started eating one another, and it was time to cover up and get an exoskeleton. So this is what we see here. And we even find in North Greenland, we find impressions of soft-bodied organisms. They're found three places on Earth, and one of them is in Greenland, where we actually have preservation of the soft parts of very early animals. And this is from a period called the Cambrian explosion, where all the phyla of the present-day Earth were formed during a very short, very brief explosion of different life forms. And all the ancestors of every critter that lives on the planet today can be found in these shales as impressions of their soft body parts. So that's extremely exciting. So if we go further up, as I said, we also find the first animals that go on land and so forth. So we have this whole record of how life has evolved through billions of years on the surface of our planet. So the place where we find these soft-bodied organisms, as you saw before, if you turn around and don't stick your nose down into all these little fossils, it looks like this. And this is another issue I think is very important that we oftentimes forget when talking about the Arctic research. We have all been very excited telling about all our wonderful results and all the data we have accumulated. But I think one thing that's particular to the Arctic is that it's so vast and majestic and so overwhelming that nobody knows to handle a view like this. You turn around and you are just completely flabbergasted by this. And I think that is another very important research driver in the Arctic that we shouldn't forget about in our excitement about all our nice quantitative data, is that the Arctic is also a source of inspiration and awe and every these other things that are the reason why we are researchers in the first place. So I think this grandeur of the Arctic nature is also a very important part of this. And we have examples of that through history, how exposure to the Arctic changed the world in many different ways. We see here an early explorer sitting in a tent and having a fun conversation with the locals. This is Fridtjof Nansen, who was the first to cross the Greenland ice cap and the first to define continental ice caps as existing altogether. And Nansen spent, as you all know, a better part of his life in the Arctic and did all these wonderful things. And sitting out there and meeting strange people and having a fun time with them and being exposed to this fantastic wealth of natural beauty probably left him rather touched. And when he came back, he founded the League of Nations, which later was transformed into the United Nations. And I think, again, it could be a coincidence, but it probably isn't a coincidence that people who are exposed to these fantastic extremes in their life, they tend to ponder a little bit deeper than many other people do. Here's a person you can see, he's already pondering here. This is a photo taken in northeast Greenland in 1906. And this is a man called, just a second, Alfred Wegener, who was a climatologist and a meteorologist. His work in the Arctic was to document the climate, and he spent many, many years was one of the first proponents of orbital forcing as one of the reasons for the change between glacials and interglacials. Alfred Wegener now is most known for one thing that has nothing to do with his primary research field, and that is when he was up there in northeast Greenland and subjected to all this fantastic geology and nature, he got this heretic idea that the continents on the surface of the planet are not stagnant and stuck to one place, but they actually drift over the surface of the planet. So he became the father of plate tectonics. He was completely ridiculed at his time, and the president of the American Association of Sciences characterized his presentation after a conference where he presented the ideas of plate tectonics with the three words "utter damn rot." That was the only comment he got, and everybody laughed him out of the room. Of course, it turned out to be correct. So again, an example of how subjecting to the Arctic can lead to unexpected and wonderful results. And one of the reasons for that is, of course, when you look at this map, we have seen many maps delineating the Arctic, but this is almost a delineation of the Arctic. This is busy part of the world. Everybody is buzzing around. There's light even at night everywhere. There's no peace and quiet. And this is the Arctic. This is the zone of peace and quiet and contemplation. And I think there's a quality to that. That means that people, first of all, they're not ridiculed before they've thought through their idea, so they can actually let it mature and get somewhere. And also that basically you have peace and quiet. And that's a quality of the Arctic that we are losing at a very rapid pace, unfortunately, it seems. So here is I think this is a good science institute. This is a good place to contemplate about the functionality of the Earth and everything else. This is the tent in the Arctic. That is where you want to be. And again, just another breathtaking view of the Arctic. And I think it's important that we acknowledge this as a special quality. Again, here we can see on full scale all kinds of interactions between natural components, like we have the basement, we have the erosion, we have the flux of nutrients to the ocean, we have the production of biomass from this nutrient-rich waters, and we can even observe those who have some fun with all this biomass that comes out. And I think this is a rather important issue that we should think about. And that is because in a congregation like this, we are all in agreement that science is important, but if we go out in the world around us, it turns out that very few people actually want to listen to what we have to say. It turns out that the political compliance is very low. We think that most people share our view that life evolved through natural selection and that climate changed by anthropogenic effects and whatnot. But it turns out that those ideas are not widely accepted, actually. And I think one of the reasons why we have this situation, we are in this situation, is that we are very good at explaining our results, but very, very poor at explaining why we are going out to obtain them. And that is due to the passion for all this. I think that it's one thing we should remember. If we want to sell our results to somebody, we have to also acknowledge that the reason why we go there is because we are passionate about the Arctic and not because we want to be the first messenger of some other bad news, which is usually what happens when we come back with our results, is that we come back and say, "Yoo-hoo, I have even more bad news than the guy before me had about the future of the planet." So I think that the Arctic has more to offer than just the specific topics of our research. So I think, again, Arctic research has, for many years, dealt with global issues more than just Arctic issues, and we should remember always to link in the Arctic experience to the global consequences, and remember again that the contemplation in the Arctic allows us probably to find some new questions, and as Einstein once said, science does not propagate by accumulation of more data, but by the formulation of new ideas. So I think with that I will complete my little talk here and hope that you have got an appetite for more of the Arctic. So thank you.